All right, so today what we're going to go over is heat capacity. Okay, now heat capacity has to do with a lot of stuff that we talked about when we were talking about climate, which was the week before Christmas. So if when I say the word climate, you're like, Mr. Cooder, you didn't teach that, it's because you haven't watched that part yet. Okay, so heat capacity has to do with many of the ways that weather happens, okay, and also the way that things heat up. Okay, so heat capacity is the amount of heat required to raise the temperature of an object, okay, by 1 degree Celsius. Okay, it's of an object. Specific heat capacity is of specific material. Right? So heat capacity, all you really need to know is the definition. We're never going to do anything with heat capacity in general. We are going to deal with this. Okay? We're going to deal with specific heat capacity a lot. Okay? So this is definitely the important one. Right? So specific heat capacity is a physical property. If you think back to chemistry, we did a lab where we used the physical properties of unknown materials to identify them. Okay? Specific heat capacity is a physical property, and it is specific or different for each material. So every material, every element, every compound has a unique specific heat capacity. Okay? Now, the specific heat capacity of an object is the amount of heat, thermal energy, required to raise the temperature of 1 gram of that substance by 1 degree Celsius. Okay? So specific heat capacity deals with a specific material, a specific mass, 1 gram, okay, and a specific change in temperature, 1 degree Celsius. Okay. Here's how specific heat capacity relates to climate. One of the biggest factors affecting climate was how close a place is to an ocean. You guys remember us talking about that before Christmas? Proximity to oceans affected climate. So as an example, Calgary and Vancouver have very similar latitudes. They're about the same distance from the equator. Our altitudes are considerably different, but our latitudes are about the same. But Vancouver is considerably more mild than Calgary. Okay? In fact, its climate is quite regular compared to Calgary, where we can go up to plus 40 and down to minus 40. That never happens in Vancouver. Okay? Their biggest temperature swing, okay, might be, it gets to be minus 5 or 10, okay, and then it gets to be like plus 25, maybe plus 30. Okay? Most of the time, the temperature in Vancouver stays pretty steady, and that's because it's next to the ocean. Water has a very high specific heat capacity, which means it can lose or gain quite a bit of thermal energy without changing its temperature very much. So if you're in Vancouver and the air temperature starts to drop, energy will naturally flow out of the ocean and into the air because of the second law of thermodynamics and keep the temperature of the air close to the temperature of the water, which is why it rarely drops below freezing in Vancouver, okay? Because the ocean doesn't freeze over there. Okay? So the air temperature is very rarely going to get colder than the ocean. Okay? Did everyone kind of follow my reasoning there? Okay? So for water, for example, okay, water has a specific heat capacity of 4.2 joules per gram degree Celsius. That means that to heat 1 gram of water, which is 1 milliliter, okay, it's a very small amount of water, by 1 degree Celsius would require 4.2 joules worth of energy. Okay, now, you're probably looking at that number and going, 4.2 joules doesn't seem like a lot, Mr. Cooder. And you're right. 4.2 joules is not a lot of energy. But we're also talking about an incredibly small amount of water and a very, very small temperature change. 1 degree and 1 gram. Okay? That is a lot of energy for that amount of water. Okay? Everyone okay with that idea? Okay? Other materials have much lower specific heat capacities. Metals, as an example, generally have very low specific heat capacity. So if I had 1 gram of aluminum, okay, instead of requiring 4.2 joules to raise the temperature by 1 degree, .9. Okay? Aluminum heats up pretty quickly. Iron's even lower. Steel's even lower. Okay? Lots of metals. Copper, exceptionally low. Okay? Copper heats up very, very quickly. All right? So these are things that can heat up very quickly because they don't require a lot of energy to change their temperature. Everyone kind of follow what specific heat capacity is? Okay. Now, what we typically do with specific heat capacity is we do some calculating. So we have this formula here. Okay? This formula deals with the amount of energy required to heat a certain amount of something by a certain amount of degrees. Okay? So E is the energy in joules. Okay? M is the mass in grams. So we're back to grams, okay, in case you didn't notice. Everything in physics was in kilograms, but this is chemistry, so it's back to grams. Okay? And then delta T is the change in temperature. Okay? And delta always means final minus initial, and obviously it would be in degrees Celsius. Okay? Is that going to be a pretty easy formula to manipulate? Like right now it solves for E. If I wanted to solve for M, what would I do with C and T? I'm already multiplying. If I want to move them, I would. What's the opposite of multiply? I divide them over to the other side. Whatever I want to leave, I leave, and I divide the other things over to the other side. So I'm looking for M, I divide C delta T over. If I'm looking for C, I divide M delta T over. If I'm looking for delta T, I divide M and C over. Okay? It's a super easy formula to use and manipulate. Okay? So specific heat capacity questions are really easy. Okay? All you basically have to do is write down your givens, manipulate the formula, plug and solve. Okay? And the manipulation is really easy. Okay. So the big thing with specific heat capacity is it can be applied to things like climate, okay, and energy transfers and things like that, and then there would be some problem solving. Okay? All right. I want you to write this one down. We're going to walk through it together. Okay? Like I always do when I give you a new formula, I do one problem for each form of that formula. Okay? So write this one down and we'll walk through it together. Sorry, I'm going to bring it back up in just a second. Yep.
What does C stand for when you put it?
Specific heat capacity.
Okay.
Sorry, I didn't say that. So, good question. Yeah, C stands for specific heat capacity. The numbers I was just looking up
Okay.
to go through. Okay, sorry. Get that one written down, guys, and then we'll go through it together. Okay, so for this one here, okay, if we're looking for how much heat, okay, we are looking for the amount of energy, E. Okay? We're trying to raise the temperature of 150 grams of water. So they gave us the mass, 150 grams. Okay? And the specific heat capacity, C, of water is 4.2 joules per gram degree Celsius. Okay? Now, you can find the specific heat capacities of most substances that we would need on the first page of this unit's worksheet booklet. All right, so that's what I was looking for there just a minute ago. Okay, so you can see lots of different specific heat capacities are listed there. Okay, that's where you can find them. Obviously, you we don't have any Wi-Fi today, so if you're trying to pull that up on your phone, you're gonna have to do it on your own data, sorry. Not my fault, but I'll apologize anyway, okay? Okay, so we have that, and we're trying to raise the temperature from 5 degrees to 85 degrees. So what's my change in temperature? 80 degrees Celsius, yeah. Okay, so I have M, I have C, I have delta T. I'm looking for E. This is about the easiest question I could get to do with specific heat capacity, because all I have to do is plug in my numbers. Okay, so I would take my 150 grams times 4.2 times 80 and punch it in. All right, so we're looking at 50,400 joules. Okay, everybody all right with that one? They don't get much easier than that, okay? And one of the biggest types of questions in this unit, okay, is one that we'll probably look at on Thursday, and it's basically this, okay, like 3 out of the 4 steps are this. Okay, so it's pretty straightforward. Okay, actually we might even look at it today. All right, everyone okay with this one? Okay. All right, write that one down, and then we'll walk through it together here in a minute. So in this one, they want to know what material this stuff is made out of, which means I'm looking for a physical property, which means I'm looking for this, because this would be specific, as it's the specific heat capacity, to the material the cup is made of. All right, we know the mass of the cup is 100 grams. Okay, we know that it takes 4,200 joules worth of energy, so they gave us E. Okay, and we're raising its temperature from 12 degrees to 62 degrees. So what's my change in temperature? 50. Okay, so now I've got that. All right, I know I'm going to be using E equals MC delta T. Okay, and so that's going to mean that I need to manipulate in order to get C by itself. Since everything is being multiplied, I'm just going to divide M delta T over to the other side. Okay, only thing you have to be careful of is that you make sure you do the bottom like separately. So like in brackets or something on your calculator. Okay, equals C, so that's going to mean 4,200 joules divided by 100 times 50. Right, so on my calculator, I would want to make sure that operation was in brackets so that it gets done first. Whoa. Oh, I got two multiplication symbols in there. Where it doesn't know what to do. Okay, so it's telling me that the specific heat capacity is 0.84 joules per gram degree Celsius. Those are the units for specific heat capacity. Okay, it's the amount of energy for 1 gram by 1 degree Celsius. So joules per gram degree Celsius. Okay, so now what I need to do is go to my list. 0.84 is glass. Okay, so this material, this cup, is made out of glass. Okay, I don't see anything else that's 0.84. Something that's 0.836, but you can't make a cup out of carbon dioxide, so okay, that one's pretty much out. So yeah, it's got to be glass. All right, so then I would write in here, okay, glass. Right, everybody okay with that one? That's how I would ask one that asks for specific heat. I wouldn't ask what's the specific heat capacity, I would ask what material is it, and then you would have to go back to your list.
We have to memorize.
You do not need to memorize that list. Okay, on both the unit and final exams, I give you all the specific heat capacities that you need. Okay. All right, write that one down and give it a try. Okay, it's got one extra step. Actually, you know what? We'll just walk through it together because it's got one extra step we haven't done yet. So this one is asking what the final temperature is. Is final temperature part of my formula? It's not. But change in temperature is. And we know that change always means final minus initial. Okay, so I don't know what delta T is, but that's what I'm going to look for first. Okay, I do know what the initial temperature is. It's 7 degrees Celsius. I know that the mass is 185 grams, and I know that there are 200 joules worth of energy being used, and it's iron. Okay, so if they tell me that it's made of iron, I can just go to my list and look up iron. 0.460 is the heat capacity of iron. All right, so I've got M, I've got E, I've got C, so I can solve for delta T. So that's what I would do first. All right, so to do that, I would just divide both sides by M times C. Okay, and so that's going to look like this. 200 joules divided by 185 times 0.46. Okay, so my temperature change Okay, so my temperature change is going to be 2.35 degrees Celsius. All right, and I was heating it up. So that means the temperature is going up or down? Up. Okay, I started at 7. I'm going to change the temperature by 2.35 degrees. What's my final temperature?
9.35 degrees.
Right. 9.35 degrees. Okay, delta T equals initial temperature, equals final temperature minus initial temperature. Sorry, guys. Okay, so if I wanted to find the final, I would take delta and add T to it. Right, I started at 7 and I heated it 2.35. 7 plus 2.35 would give me my final of 9.35 degrees Celsius. That's as tricky as they get. That extra step where you had to add them. Okay, so it's not like a super tricky extra step, but it's there. Okay, everybody with me on those? Okay, so these are not going to challenge us mathematically or intellectually, for that matter. Okay, because they're pretty straightforward. Oh no, don't do that today. Okay, I would like you guys to do let's say for right now, the 3 that are circled there. Okay, since you might not be able to call it up on your phone right now because the Wi-Fi is probably still down. Okay, do 1, 3, and 4. Okay, then I'm going to pick a couple more and have you do those. Okay, so 1, 3, and 4 are all the same manipulation. Okay, 1, 3, and 4 are all asking you to calculate specific heat capacity. Okay, so let's get to work on 1, 3, and 4. Probably have those done in no time at all. Okay, so I just posted in Google Classroom a supplemental review sheet. It's got 6 problems on it. Okay, so there's 2 graphs. Okay, and unlike the graphs that were on the first review package, these ones are linear and have y equals mx plus b. Okay, because the 2 graphs that were on your unit review did not. Okay, so you didn't get any practice with those, so these two are the opposite. Okay, there's a position versus time graph and the velocity versus time graph, and it's going to ask you to use the equation to calculate some stuff. And then there is a acceleration problem. There are two work energy theorem problems, and there is a law of conservation energy problem. Okay, so like what's going to be on your test, okay, like I told you before Christmas. Right, so if you've already done the review sheet and you want some fresh questions, they're in Google Classroom now. Okay, you can check them over tonight. Probably won't take you very long to do those, but probably worth doing if you're looking to study something tonight to prepare for your exam tomorrow. Okay. All right, so let's move on to latent heat here. Okay. We talked about latent heat back when we were talking about how energy moves on Earth. Okay? One of the ways that energy can be transferred from the equator to the poles is through air masses that are carrying water vapor. Okay? That energy that's in the water vapor is called latent heat. Okay? And that's because we don't feel it. It's energy that's stored in water because it's a gas and not a liquid. Okay? Does it take energy to turn water from a liquid to a gas? It does, right? It doesn't just happen on its own. It heats up, okay, and then it turns into a gas or into a vapor. Okay? Now that energy is carried with the water vapor to a new area. When that water vapor gets there, it condenses, and when it condenses, it releases all the energy that it had stored as a result of being a vapor, because it's no longer a vapor. It's condensed back into a liquid, and now that latent heat becomes sensible heat. Okay, and it's part of the reason for that that's part of the reason for weather changes that occur kind of right before a thunderstorm or as a hurricane approaches. Okay, back in the late fall, when the big hurricane came up the coast there and it hit Atlantic Canada, okay, they actually went from having quite cold temperatures right before the hurricane to like the day and a half before the hurricane, suddenly it got really, really warm. Okay? And that's because all this water vapor was coming with the hurricane. It was condensing, falling as rain. It was releasing a lot of sensible heat into the area, which brought the temperature up. Okay, in that area. So we generally feel that, okay, whenever water vapor is going to condense. You may have heard this when you were a kid, okay, when they were teaching you how to be safe in the kitchen, that steam can burn you worse than water. You guys heard that before? Okay, like you wouldn't want to put your hand in front of a tea kettle with steam coming out of it. Okay, now most people just think, well, it's because steam is hotter than water. Well, it doesn't have to be. Water can be 100 degrees Celsius, and so can steam. They coexist at 100. It's where they turn into each other. But steam at 100 degrees Celsius carries far more energy than liquid water at 100 degrees. I'm not saying dip your hand in liquid water at 100 degrees Celsius. That would be crazy. You would burn yourself. But steam at 100 degrees would give you a far deeper burn. Okay? And that's because when the steam hits your flesh, it condenses back into a liquid. So first, it burns you because it's 100 degrees Celsius, and that's really hot. And then, when it condenses, it releases all the latent heat that it had stored, and that becomes sensible heat, which results in a much deeper burn. Okay? So it releases a lot more energy, which is why you have to be more cautious of steam than water. Okay? Everyone kind of follow me on that? Okay? And the reason is right here, this graph. Okay? This graph is what we call the heating curve for water. Okay? All materials have their own heating curve, okay? But they all generally have a shape similar to this. Okay? They have an upward part, a flat part, an upward part, a flat part, and an upward part. Okay? So they all kind of have this shape. Where the flat parts are is dependent on what material you're dealing with, because all materials have different melting and boiling points. Okay? Whenever the state of a material changes, the temperature stops changing. Okay? The weird thing about thermal energy is that you can't change both kinetic and potential thermal energy at the same time. Okay? If we're talking about mechanical energy, I can totally change kinetic and potential mechanical energy at the same time. Okay? I accelerate something upwards and I'm changing both. Thermal energy doesn't work that way. I can change the kinetic thermal energy of a material, and if I do that, it'll get hotter. Its temperature will change. Or I can change the potential thermal energy of the object. When I do that, what I do is I make the particles move away from each other. So in a solid, the particles are tightly packed. Okay? You guys learned that back in junior high, right? So in a solid, the particles are tightly packed and they move around. Okay? When it turns to a liquid, whatever that material is, the particles move apart. Now they can move past each other, which is why liquids can flow and solids can't. Okay? So they can take the shape of their container. But to move them apart requires energy. That's a change in potential energy. If that material freezes, they'll go back together again, and the energy they had will be released. Okay? You see this in the fall, when just before lakes freeze. Okay? I don't know if anyone's ever seen this, but in the fall, if you go to the lake, you'll see steam coming off the lake, even though it's really cold outside. That's that lake starting to change state from liquid to solid. Okay? And it's releasing sensible heat around it, so the temperature just above the lake in the air is actually a bit warmer. Okay, because that lake is now releasing some of its latent heat. Everyone kind of follow there? Okay, so if I've got a liquid and I heat it up, I can still make the particles move farther apart and turn that liquid into a gas. Okay, and gases are even more fluid than liquids are. Okay, the particles are even further apart. So every time I move the particles apart, the temperature stops changing. Okay, this is why we put ice in drinks if we want them to stay cold. As long as the ice is there, the drink will stay around the freezing point of water because energy will be flowing from the drink into the ice, trying to melt the ice. Okay? But as long as the ice is present, the temperature will remain the same. As soon as all the ice is melted, the temperature will start to go up. Only one kind of energy can change at a time. Either kinetic thermal energy, which makes temperature go up or down, okay, or potential thermal energy, which makes particles move apart or closer. Okay, everyone follow there? So for water, okay, the melting point, freezing point, is 0 degrees Celsius. The boiling point or condensation point is 100. Okay, you guys all knew that already, yes? That's not new information. Okay, all right. So if I have a block of ice, and let's say I've taken like an ice cream pail and I've frozen all the water in it, so now I have a big block of ice. Okay? And I put it in a pan, I turn on the stove. What's going to happen to the ice? Before it melts, what does it have to do? Because it won't melt until it reaches what temperature? 0. So first, the ice has to warm up to 0 degrees Celsius. If you take something out of your freezer, it's probably between minus 15 and minus 20. Okay, that's typically what your freezer would be set at. Okay, so if you take that thing out and put it in the pan, the ice is below freezing. Okay, you have to heat the ice to freezing, and then it will start to melt. Okay, so the first part of that process is actually changing the kinetic thermal energy of the ice to get it to 0. Once it gets to 0, it'll start to melt. If you put a thermometer in that pot while that ice is melting, the thermometer will stay around 0 until all the ice has melted. Okay, now, you have to stir it, because if you allow it to stratify, yes, nearest to the burner will get hotter than that. But if you keep stirring it, the mixture will stay around 0 degrees. Okay? So it'll stay there until all the ice melts. And then the temperature will start to go up, because you continue to add energy. Okay? So the water continues to gain energy. Then it'll get to boiling. Well, liquid water can't get hotter than 100 degrees Celsius unless you pressurize it. And you're not doing that, you've got it open. Okay? So it'll sit there and boil and stay at 100 degrees Celsius until what? Till all the water is gone. Okay? It'll actually sit there and boil away, but it'll never get hotter than 100 degrees. Okay? Now, if you could contain the steam, okay, as it evaporated, would the steam start to get hotter once all the water was gone? It would. Okay? This is how a pressure cooker works. Anyone have a pressure cooker, like an Instant Pot? at home, okay? You can use it as a pressure cooker. When you crank on the lid, okay, you can build up the pressure, which means you can get the liquid water inside hotter than 100 degrees Celsius because you're putting it under pressure, and that raises the boiling point of the water. That cooks things faster. Okay, it's also why deep frying things cooks things faster. You can heat oil to a much higher temperature than you can water, because the water will start to boil and it'll boil off. The oil won't, so deep frying things cooks faster and tastes better. Okay, all right, everyone kind of follow here. All right, so we just learned a few minutes ago this formula here. Okay, this formula calculates the amount of kinetic thermal energy change. Okay, that's why it has delta T in it. Anytime you're changing the temperature of something, you are changing the speed at which the particles move. Okay, the more heat, the faster they move, regardless of their state. Okay, so anytime I change the temperature, I change the kinetic thermal energy of that material. So if I wanted to calculate the amount of energy required to heat ice from minus 25 to 0, I would use this formula, because I would know how much ice in grams. I would know the specific heat capacity of ice, which is not the same as water. Strange but true. Water is, again, one of those weird things. Okay, and I would know how much I have to change the temperature by. From minus 25 to 0 would be how many degrees? 25. Okay, everyone follow me there? So anywhere on this graph where the line is diagonal, I use this formula. I can't use that formula for the other two parts of the graph, because if I do, it will tell me the energy change is what? Because during this part of the graph here, and this part of the graph here, what's the temperature not doing? It's not changing. So if I try and use this formula and I put in 0 for delta T, it's going to tell me I didn't require any energy. Well, the burner was still on, energy was clearly being put in, there was an energy change. So that formula doesn't work on these sections because it calculates the change in thermokinetic energy. During these two parts of the graph, the thermal potential energy is changing. Okay? And there's two different kinds. There's the latent heat of fusion, which happens when something can either melt or freeze, and the latent heat of vaporization, which happens when something condenses or evaporates. Okay? So, everyone okay with that idea? Okay. There's a different formula, it looks very similar, but it uses a different number for each section of that graph. Okay? There is this one. E equals MLF. M is still the mass. LF is the latent heat of fusion. Okay, and for water, that's 333 joules per gram. Okay, that number is on your formula sheet. It's on the back of your periodic table. It is not a number you have to memorize. Okay, so what that number means is this. If I have 1 gram of ice, to melt that 1 gram of ice would require 333 joules of energy. Is that a lot? You ever make a snowball with your bare hands? Hands get cold pretty fast. You don't make many snowballs with bare hands, okay? Because your hands get really, really cold. Because as you form that snowball, a bunch of it melts, and it's getting the heat to melt from your hands. For every gram of water, that's not a lot of water. For every gram of ice, that's not a lot of ice that melts. 333 joules of thermal energy are lost from your hands. They go to the ice. Okay, that makes sense? Okay. up here, we use this formula. E equals mLV. Works pretty much the same. The latent heat of vaporization per water is 2,260 joules. Okay? That means that for 1 milliliter of water, 1 gram of water, to evaporate into steam requires 2,260 joules of energy for 1 gram of water. Okay. When you got out of the shower this morning, okay, before you put on your towel, did you feel cold? As soon as the hot water goes off, right, you get out and you're like, geez, it's cold, okay? Is it really cold? The temperature of your room didn't change, okay? It's still like 21 degrees or whatever you have your house set at. It's not actually cold, but you feel cold, okay? You feel cold because you're covered in water and the water's starting to what? Like if you stood there long enough, eventually you would be, not cold, but you might feel cold, but you'd be dry, right? If you just stood there and like drip dried, okay, that would take a long time, it'd be kind of weird, but okay, if you did that, okay, eventually you'd be dry. Well, that means that the water that stayed on your body evaporated. Where did it get the energy to do that from? From you. This is how sweat works. This is why we sweat. Okay? If you're working hard, you start to sweat, the sweat evaporates. For every gram of sweat that evaporates from your body, you lose 2,260 joules of energy. That's a lot. Okay? That's why, like if you've gone to Stampede in the summertime, they got those misting stations, the cooling stations, where you walk through the mist and then you suddenly feel so much better. Okay? It's not because that water's cold. But once it starts to evaporate from your body, every gram of it requires 2,260 joules of energy from you. So you feel cooler. Okay? We're going to continue talking about that on Thursday. Boy, we got a lot to do. Okay.